Good, after- Good afternoon, everyone. I will be talking about our work on online learning in kernelized MDPs. So the problem setting was to episodically maximize the reward in an unknown Markov decision process. The reward distribution and the transition distribution is unknown. And we consider the state and action spaces where they are continuous and they are subspaces of multidimensional Euclidean spaces. So the challenge is to generalize across these continuous state and actions, and for that we need some regularity assumptions. We assume that mean reward and mean transition functions are elements from reproducing kernel Hilbert spaces. And the learning framework is to just at the start of every episode, whatever data you have, based on that you choose a policy to follow for the entire episode. And our goal will be to minimize the cumulative regret, and that is the loss incurred due to not knowing the value function and not knowing the optimal policy, and play some policy chosen by the algorithm. So how we do design our algorithms? We use Gaussian process regression. We put separate Gaussian process priors over mean, reward, and transition functions, and update posteriors at the end of every episode. Whatever data we have, we update the posteriors of the mean, reward, and mean transition functions GPs at the end of every episode. And based on this posterior GP in hand, we give two no regret policy selection rules. One is based on upper confidence bound reinforcement learning algorithm, but here we use GP, so we would name it as GP UCRL. Another is the randomized strategy called posterior sampling in reinforcement learning. We show that the average regret goes down to zero as number of rounds tends to infinite. One application of this work will be to linear quadratic regulator control problem, where the transition dynamics follows from a reproducing kernel Hilbert space with linear kernel, and the rewards will follow from a reproducing kernel Hilbert space with a quadratic kernel. Yeah. Thanks. Please come to our poster for more details.
Okay. Most tasks that you might encounter have sequential structure between goals, and there might be temporal deadlines, and there might be time-varying obstacle constraints. These are very challenging problems to solve if you just have one reward function defined on the state. That reward function generally doesn't carry task semantics, and therefore the value function that you derive from it also doesn't carry task semantics. But I can show that it is possible to infer an optimal non-stationary policy to satisfy sequences of goals. And to do this, you have to create a new type of Bellman equation. Okay, so what you'll need to do is you have to pre-compute low-level dynamics. You have to extract time-to-go information from those dynamics. And then you can use that reachability information in a reachability Bellman equation that tells you what stationary policy in your pre-computed dynamics to use at what time. So these feasibility functions are really nice because you can chain them together and you can quickly evaluate whether sequential goals are feasible. And so you can solve problems. You can solve problems where the environment is changing and you want to hit all of these green squares before they disappear. So you can change the environment, and yeah, you can solve this exactly, and it's very good for generalization. Okay, thanks.
Hi. So we have this new model of hierarchical control that we presented last ICLR. It's like the options framework, except with more features. We think of options as procedures calling other procedures, so they push them onto a call stack. When a procedure terminates, it pops from the call stack. And now we need to control that stack to exert our hierarchical control. And the problem is that we're going to do it with imitation learning, where we don't get to see in demonstrations this call structure. So we need to infer it, but it's a huge it's a huge latent space, particularly because we're going to have procedures pass arguments to other procedures and also return values when they terminate. So that's going to make it very large. So we're going to use variational inference, and we have the elbow, and so we have this nice architecture for both the controller and the posterior controller for inferring the control structure. And because everything is also discrete, we find that we need some tricks, extra tricks to make this variational inference work. So please see the poster for the details. Thank you.
Hi, I'm Matthew Fellows from Oxford University, and I'm presenting Viral, a new model that recasts reinforcement learning as inference. So from the graphical model, we see that our observed variable is related to the optimality of the reinforcement learning problem. However, unlike previous models, our hidden variables are state-action pairs. Key to Viral is the likelihood distribution, which is defined as the exponential of the Q function under the action posterior divided by the mean squared Bellman error. This affords the important theoretical result that maximizing the log marginal likelihood of the model is equivalent to minimizing the mean squared Bellman error, and consequently, the action posterior learn becomes a greedy policy with respect to the Q function. This means that we learn optimal policies for the reinforcement learning problem. So what are the benefits of using Viral? Well, as we've shown, it's theoretically grounded with exact correspondence between theoretically grounded learning greedy policies, and we also demonstrate an exact correspondence between expectation maximization and actor critic. We learn underlying dynamics of the Markov decision process using Q functions with no implicit dependence on variational distributions, unlike work based on maximum entropy reinforcement learning. Also, the direction of our KL divergence is mode seeking so that we don't learn risk-seeking policies. Finally, we present a simple and intuitive graphical structure with high applicability for variational inference frameworks. Thank you.
Hello, I am Jonas, and I'm here to present to you quinoa, which is a Q function which you can infer normalized over actions. Now, why would you want such a thing? Well, basically the idea is that we designed a neural network architecture, and when you fit your Q function using this neural network architecture, which is in continuous action space and continuous state space, you get your optimal policy in this architecture in closed form. So if you would use this architecture to fit your Q function, basically you don't require an additional policy optimization step anymore, as you have the optimal policy which would be interested in closed form. If you want more information on how we derived this, please come see my poster. Thank you.
Hi, good afternoon. So I'm here to present our work on variation autoencoding context for control. Imagine you have a hand robot which tries to manipulate some objects, and at the very beginning of each episode, you will randomly sample an object of random shape and size. The robot does not have access to the random shape and size of the object, but needs to manipulate the object in order to infer all this information. So you can train RM policy on top of that. So what this RM policy does is to perform some implicit system identification to kind of infer about from the information of the object it's trying to manipulate. So we can think of the dynamics of the model as being determined by this hidden variable, which determines the shape and size of this object, and it's drawn from a mixture because at the very beginning of each episode we sample from this mixture distribution. We can explicitly model this distribution using variation autoencoder. So we propose to combine the computation graph of this policy optimization with variation autoencoder and pass this modeling step explicitly to the policy optimization. By doing this, we're able to allow the RM policy to carry out more efficient system identification and speed up the policy optimization. Please stop by our poster for more information. Thank you.
Hi everyone, I'm Karl Pertsch and I'm presenting joint work with Oleg Rybkin. And the main idea here is that we want to unsupervisedly learn a representation of the action space of an agent from pure visual observations only. So no action annotated demonstrations and also no interaction with the environment for this representation learning step. And the scenario you could imagine is like the one I show here on the right, where you download a couple of videos of agents performing tasks from the internet or from somewhere, and you'll learn a representation of the action space of those agents, and so that once you get access to your own robot, you can very quickly learn to perform actions and to control this robot. And the framework we're using to do this is a variational video prediction framework, where we predict future video frames with a model that has a latent variable. And so it uses a variational information bottleneck objective combined with a novel composability objective to enforce action-like structure onto this latent variable. And then at test time, we only need a couple of action-annotated sequences to learn a bijective mapping to this latent variable, and can then start to control our agent with this bijective mapping. And obviously, we don't want to claim that we solved the problem we show here on the right, but we show some results on a more toyish data set with the right agent visual features and also backgrounds, and then also on the robot, bare robot pushing data set. So for more details, please come and see us at our poster.
Hi, I'm Max. I'm going to present inference distillation option learning. The name has changed. So we think that learning hierarchical policies in a multitask setting makes a lot of sense because if we can learn movement primitives which are useful across the range of training tasks, then it's very likely that they're also going to be useful on new tasks drawn from the same task distribution. So in this work, we're trying to learn a finite set of options, including their intra-option policy and also their termination policy. Now, a challenge in learning hierarchical policies in a multitask setup is one of diversity. In particular, we don't want two or more options to learn the same behavior. That, however, creates the problem that now the higher level policies on the tasks that we're training on need somehow to coordinate, because if two options are used for the same subgoal on different tasks, then it's hard for both of them to escape that local minimum and learn something new. So how do we get those higher level policies to coordinate? And here we leverage the Bayesian idea of having a prior-posterior distribution, and that allows us to, during training time, relax the constraint that options have to be exactly the same across all the tasks during training. And what's nice is that within this framework, what also comes out is that the higher level policies are actually incentivized to pick the more specialized option. And those things together allow us to actually escape this local minimum and learn a nice diverse set of options. We have a bunch of results. It works. So the left-hand side shows that we learn more diverse options than previous work, and we also successfully apply it to transfer learning setups. Thank you very much. And our poster is in the corner.
Hi, my name is Brian Ichter, and this is joint work with Marco Pavone from Stanford University. So in this work, we present a methodology to learn a latent space in which we can directly do sampling-based motion planning in order to enable planning for systems as complex as this humanoid on the left or this visual state planning problem. So one method that's been used a lot in learning-based control, and you see around here, is to leverage local, low-dimensional learned latent spaces in order to enable planning, or in order to enable control for complex systems like this. Unfortunately, the local nature of this means that it can't be used particularly well for long-term global plans. Another thing that's used in the motion planning community is sampling-based motion planning, which essentially avoids the explicit construction of the entire state space and instead builds just an implicit global representation of the state space through only local collision-free connections. Unfortunately, this doesn't scale to things like these 50-dimensional, very complex systems or the 1,000-dimensional pixel space. So the key idea that we take away here is that we can actually, because this is only built off local collision-free connections, we can actually use these learning-based representations that are only local in order to build a global representation in the latent space. So the idea is to learn a latent space where we enforce all the algorithmic primitives of sampling-based motion planning, in particular an autoencoder so that we can sample, a latent dynamic so that we can do local connections, and then we learn a separate collision checker in order to do the entire planning algorithm in latent space and then project back out to get plans like on the bottom right. And I've also got a poster in the corner. I think that's everybody.